So I like what you wrote in there. You started to talk about, hopefully I'm not too high, this velocity clock reading graph.
Mhm.
And the first thing you wrote up in, and let me get back to that, you wrote the area of a VT graph equals the displacement, right?
Yes.
So let's go ahead and annotate that real quick. You said the displacement is this area.
Yes.
So let's look at that real quick. So area, so if we want to find the area of a triangle, we'd probably say something like 1/2 base times height. Is that fair?
Yes.
All right. And so we have to kind of define what's going on here. I'm going to call this side of the triangle the base. And I'm going to call this side of the triangle the height. Is that okay?
Yes.
All right. So the base, though, isn't just some random number that we're going to choose. It's actually going to be this time interval. Okay, it's the time interval for it to travel this displacement.
Okay.
So I'm going to go ahead and put that in. So we know the displacement, which is the area, is 1/2 the base, which is the time it takes to travel. But then we also have the height here, which I go from 0 to some final velocity here. But we don't really know what that is either. So this is the final velocity. Okay? So I can put that as the height. Does that look okay so far?
Yes.
All right. Now, in all of your trials, what displacement did you use for the whole thing?
0.9.
Okay, so we're going to replace that. 0.9 meters equals 1/2. And then did you have a certain time you wanted to use?
Yeah. Well, it was about 0.98 seconds.
Okay, I'm going to write that in. 0.98 seconds. And then we don't know how fast it's traveling at the end here. Okay. What some students like to do, what they like to do is they would now make a data table, something like the time and the final velocity. So it sounds like you said, in fact, maybe I'll do it this way so we can stay the time. And it sounds like you said the time was 0.98 seconds for this, right?
Yes.
So what we could do is we could just use our algebra, get rid of that and that. We can just use our algebra and multiply both sides by 2. 1.8 equals 0.98 V final. So V final, divide both sides by 0.98.
1.9. 1.8.
1.8?
Yeah.
Okay. So I'm going to write it here, 1.8 meters per second. Okay?
Okay.
So I'm going to pause there, and now I'm going to go ahead and look at what you said in the second line. You said, when I read it, it says the slope of a VT graph equals the acceleration.
Yes.
So let's look at the slope, which is acceleration. So let's look at slope. And slope, we know, hopefully, is rise over run. Is that fair?
Yes.
So in your comment, you said slope is acceleration. The rise of this, if you notice, the rise, we start from 0 and we go up to some final velocity.
Mm-hmm.
So I'm going to say the rise is just the final velocity. Is that looking okay?
Yeah.
And the run is how much time it took.
So 0.98.
Correct. Now we can plug in our numbers. You said, I heard you say, okay, so we know the final velocity is 1.8. So I'll write that in. Final velocity is 1.8 meters per second. And the time interval, which we had, was 0.98. And then when we do that, we get an acceleration of 1.8 meters per second every second.
Okay, that makes a lot more sense.
So I'm going to go ahead and add a column here of A. Actually, let's keep this. A 1.8 meters per second every second.